Okay, let's get started. So, we are learning about the GPU memory hierarchy, and and then in the previous class we learned about the detailed memory component of the GPU processors. So actually, I mentioned that in a GPU core includes the different kinds of private caches. So actually, I believe you are familiar with the instruction cache or level on data cache. So GPU also has the instruction cache, level on instruction cache, and then instruction fetch engine fetch the target instruction from this instruction cache. Okay, and it's very normal for the processor. But GPU has its dedicated caches such as the constant cache, texture cache, and then data cache. Data cache is used for the cache memory for general data. Actually, I mentioned that the GPUs are originally designed for graphics application. That's why GPUs has these dedicated caches like text cache or a constant cache. But GPU also recently GPU has the general level data cache. Then and like here, so it means that the cached data is automatically managed by GPU hardware, not software. Also, GPU has the shared memory. And then, as I mentioned, this shared memory is the scratchpad memory. So I mentioned that the programmers can manage data in scratchpad memory. So you can distinguish this scratchpad memory or general data cache, such as if the data in the memory are managed by programmers and it's called the scratchpad memory. Then if the data in the cache are managed automatically by hardware, not programmers. Okay, so it's also it's out of the topic of the discourse, but if you are interested in the accelerator architecture, then you can also include the scratchpad memory or normal data cache, which means if the accelerator has the scratchpad memory, then programmers can the contents in the scratchpad memory. So manage the contents in the scratchpad memory. But if the accelerator has the normal caches, then these contents in the caches are automatically managed by hardware. Okay. We can select some different approaches for this memory hierarchy of the accelerator architecture. But the GPUs, so actually GPUs, so nowadays GPUs are used for running general purpose applications. So GPU has its own level of data cache. So for the general purpose application, the GPU hardware can automatically manage the contents in the data cache. But actually the cache hierarchies exploit the locality, the data locality. So there are two kinds of locality, like temporal or spatial locality. So actually the CPU hardware manages the contents in the data cache using the locality of the locality observed in the applications. And then I also mentioned that the GPU, this is the overall architecture of the GPU processor. The GPU also includes the multiple stream multiprocessors, and then also GPU has the multiple L2 partitions. Then also these partitions are directly connected to the external memory, the device memory of the GPU. So you can find that there are multiple memory controllers. Okay, which means that a single GPU chip includes the multiple memory channels. So it is because the bandwidth is more critical for the performance of GPU. Okay. So we can classify some different kind of memory hierarchy of GPU processor, like register, and then so the shared memory, constant cache, text cache, also the data cache. Also, GPU has the multiple memory spaces like this. Okay. So actually, if you see the to the code, then you can find some primitive in the code. So actually, so we can declare, the programmers can declare the required memory space for each variable. Okay, using the CUDA primitive. Okay. So this the file is very large, unlike the CPU. Constant cache, text caches are a dedicated cache for the specific application. So actually, we can frequently use the constant cache because we can use the parameters. If some parameters are shared by multiple threads, and then if these parameters are read-only data, then we can use the constant cache. And then text caches are used for textual mapping, but it's only for the graphics applications, not the general purpose application. Then also we can use the shared memory. Okay. So now, I will explain about the load store unit of the GPU. So actually, the load store unit is the execution engine for the load and store instructions. Right? It's the same for the it's the same to the CPU. Actually, the CPU you can find the load store unit, the CPU core, and then actually the load store unit of the CPU core also execute the load and store instructions. But actually the CPU supports the out-of-order processing. So the modern processor, actually modern CPU supports the out-of-order processing, which means that the order of the load and store instructions can be also out of order inside of the CPU core. But the GPU core is much simpler than the CPU cores. So actually, I also mentioned that the instructions in the thread are executed in order in the GPU core. Okay, and then also, but GPUs can hide the latencies in each instruction using fine-grained multithreading. Okay, so but let's see the load store unit. So actually, the load store unit is somewhat different from the architecture of the processor engine, the GPU core. A little bit code. So the load store unit, the load store instructions need to access the cache first, and then firstly the load store unit access the cache, and if the data is not found in the cache, then this transaction or memory request are delivered to the interconnection network. Okay, and then these transactions are given to the idle cache of the GPU. But I said that in the GPU streaming multiprocessor, there are multiple warps. Okay, there are multiple warps here, and then warp scheduler decides each warp will be issued to the execution engine. So it's the same to the load store unit. If the current warp, so selected warp has the load or store instruction, then this warp is issued to the load store unit. But problem is that, so actually when we learned about the core architecture of the GPU, so we learned that the GPU has the multiple CUDA cores. So CUDA cores is the kind of processing engine, so which means that each CUDA core is associated with the thread in a wire. Okay, so usually, so AMD or NVIDIA GPU has 32 threads or wire, which means that when a warp is executed, the threads in the warp are associated with the 32 processing engine, and we can execute these instructions in parallel. But the problem is that this cache, the transactions to the memory hierarchy to the of the GPU should be serialized. Okay, that's the problem of the load store instructions and GPU processor. So also think like this: there are many threads. GPUs can run thousands of threads concurrently, or also instead of 10,000 of cores, something like that. So if these threads generate the transaction, then it will occupy the hardware resources of this memory hierarchy. So if you run about the advanced computer architecture course, then you can know that the hardware resources of the memory system is limited. So actually the cache, think like a cache. The cache has the two ports, like here and here. The one port from the core, and then another port is to the low level cache. Okay. But the transaction to the cache is serialized, and then each transaction is including this transaction queue of the cache, and then these transactions are serially executed. So in the CPU core, you can find the load store queue, right? So actually, even though the instructions are executed out of order, actually the instructions, the load store instructions are serially executed using load store queue. So it is because the cache, like this memory component, has the limited hardware resources, such as the limited number of ports, also limited number of blocks. Obviously, the cache size is limited, so it's very small compared to the main memory. Also, cache also has the MSHR to support the non-blocking cache, but the resources in the MSHR are also limited. So these hardware resources are limited, but if a single SM execute the multiple thread concurrently, then these multiple threads can occupy the all hardware resources in this GPU memory hierarchy. And this is very bad for the performance of GPU. So actually, so we already know that the load instruction is the critical performance bottleneck in the processor, right? Because actually data movement cost is very high recently. And then actually CPUs need to wait many cycles for load instruction, right? Because if the data is bound in the main memory, then it will take hundreds of cycles. So it will degrade the performance of a processor dramatically. It's the same for the actually GPU. So even though the GPU has supports the fine grained multithreading to hide the latency of the instruction, but using this fine grained multithreading, the GPUs can only hide the tens of cycles, right? But the memory latency is kind of hundreds or even thousands of cycles. So actually, this long latency of the memory hierarchy cannot be hidden by this GPU. The problem is that so I said that each memory component has the queue, so which means that the transaction or memory requests are included in this transaction queue. And then actually this memory is the service engine. So we can design this model like this is a queuing, like the queuing model. Like this is the queue, and then this is the some service provider. Okay, that provide some that service the request from this queue. Okay, so which means that we can also model the memory hierarchy or memory components of the GPU like this queuing model. But the problem is that the wait time in this queue, it has the horizontal distribution, that the linear distribution. So which means that if many requests are waiting in this queue, then the horizontal distribution looks like this. It's not linear. So which means that the transaction needs to wait more cycles inside of the queue. Then it will also decides the wait time or latency in the memory hierarchy of the GPU. So what's the problem? If the data traffic is very heavy, then our load instruction was even the store instruction is a little bit different, but load instruction in the GPU needs to consume more cycles. And then based on the queuing theory, it need to wait much more cycles. Okay, the traffic is very heavy. And that's also the critical performance issues in the GPU. So first, we need to reduce the data traffic inside of the GPU. So which means that we need to reduce the number of transactions or number of memory requests in the GPU. That's the highest priority of the memory system design of the GPU. Okay. So this slide shows the timeline of the load store unit. And then as you can see, this load store unit of the GPU is different from the load store unit of the CPU. So it is because the CPU executes only a single thread, and then actually the single thread will generate each load instruction of the single thread will generate only one memory transaction. So which means that if one instruction is executed in a load store unit of the CPU, then it will generate only one transaction, and then this transaction is included in this request queue. Okay, like the load queue, or if the instruction is the store instruction, then the transaction is included in the store queue. But GPU has the multiple pipeline stages like this. So actually, it is because the GPU load store unit also receives the work. Okay, so GPU work scheduler issue a single work if this work can be serviced by the load store unit. And work. The work includes the many threads. Okay, so it is different from the CPU. The CPU has only single thread. Okay, but work has the many threads. And then let us assume that GPU execute the load instruction like the load R1 and then R2 and immediate. So this is typical load instruction. So this is the destination register of the load instruction, and then this is the source register. Okay, and then let us and then a single work includes 32 threads. Then the thread as the source register, which means that this warp need to collect operand from for R2 from register 5. So when the warp is issued, then the warp is issued to the operand collecting unit. This is also the unique feature of the GPU, as I explained. So the load store unit collects the required operand, the operand collector unit, or this source register, right? And then if the operands are collected, then each thread will generate its own memory transaction, right? So this is the load instruction, like the other normal arithmetic instruction. Normal arithmetic instructions also execute each own instruction. So it's the same to the load instruction. So if this load instruction, this warp includes the storage to active thread, and the GPU needs to generate the storage to transactions, okay, for each thread. Now, what's the problem? If the GPUs are designed like CPU, then these transactions are collected, and then these transactions need to be included in this request queue of the cache, right? Then if the one warp is executed, then this one warp will generate, if there are 32 active threads, then this one warp will generate the 32 different transactions. Okay, so what's the problem? So it's only the queue. So one warp is executed, but these transactions need to be serialized, and then actually the one warp will generate the many transactions. So which means 32 transactions. So the queues, so these transactions will wait long time inside of the queue. Okay, that's the very critical for the performance of the load instruction. So in order to avoid this situation, the GPU has also its own unique processing unit. It's called the wireless. So this word wireless is the meaning of the wireless is similar to the actually merge. Okay. Sometimes the contracted is the difficult word. So actually the meaning is the same. So the meaning of wirelessing is merging. Okay. So which means that even though the multiple transactions are generated from a single warp, these multiple transactions are merged. Okay. How? Actually, we cannot merge the different transactions. Like there are multiple threads, and then this thread generate the multiple memory transaction. Actually, these memory transactions cannot be merged, right? Because this transaction will have its own request address, and then this request of its own transaction need to be serviced from the memory hierarchy of the GPU. But how can we merge these multiple transactions? GPUs can also exploit the locality of the application. What locality? Spatial locality. So think like this. How does cache exploit the spatial locality. How can cache exploit the spatial locality in application? Then, so I change the question. So how can we take advantage of the spatial locality more in the cache? 어떻게 하면은 캐시에서 우리가 더 스페셜 로컬리티를 더 많이 이용할 수 있을까? 이게 지금. How can we take advantage of spatial locality more in the cache? It's simple, right? If the cache block size is large, okay, then this cache can exploit spatial locality more, right? So think like the CPU, so which means that when the CPU executes the load instruction, then this, even though this load instruction requires this size of the data, but the cache requires the one cache line size of data, right? So for example, the cache line size of the Intel Atom cache is the 64 byte. So even though the load instruction requires the 1 byte of data, then for the cache is the one cache line, like the 64 bytes of data. Why? If this cache line size is large, then the next load instruction may request the nearby data here, also here and here and here. This is the spatial locality. So which means that if we increase the cache line size, then we can exploit the spatial locality more. How about the GPU? So actually the GPU cache line size is also large. So usually the one cache line size is the 128 byte. So I mentioned that why the cache line size is 64 bytes for Intel, 128 bytes for GPU. It is related to the burst length of the memory, DRAM memory request. Okay, so cache line size is large. So which means that if the one thread requests this amount of data, then the another thread in the same route may request the nearby data with a high probability. So this is the spatial locality, but it's same for it's true for the GPU application. Then think like this. So actually we learned about the vector add application, and then in order to access each element of the vector, then actually this each element of the vector is assigned to the thread. Okay, but when these elements are assigned to the thread GPU, actually neighbor elements are assigned to the neighbor thread. So which means that the thread whose thread indexes are very similar to the neighbor thread, right? Which means that the thread index is 0, then the neighbor element is assigned to the thread index 1, or thread index 2, blah blah blah. And then also when a walkthrough is generated, the thread which have the similar thread indexes are grouped into one. So it's obvious, right? So when the 32 threads are grouped into a work, thread number 0 to 31 are grouped into 1, 0, and then the next thread number 32 to 63 are grouped into another one. So which means that threads are, so neighbor threads are grouped into a single one with the, it's obvious. Okay, and then these usually, as I said, usually, and then if the thread indexes are similar, then these threads will access the neighbor data. So for example, because each thread will access the elements of the array data using the thread indexes, right? So which means that if the thread index is 0, then this thread will access the element index 0, and the thread index is 1, and this thread will, with a high probability, it's not arrays, then we'll access the array index 1, right? So we can observe there is strong locality between thread inside the one, and then also the GPU cache line size is large. So which means that these multiple, the requests from these multiple threads are merged in the one memory transaction if these requests can be encapsulated in the single cache line size. So for example, the cache line size is the 128 byte, like here, 0 to 127. And then if this thread access to this data, then thread number 2 access to this data, then these transactions can be merged into the one single transaction. So then the GPUs can reduce the number of transactions, the cache. Okay, this is called the memory quality. But I said that this is the example of the memory quality. So which means that the transaction from multiple threads can be lined the one cache line, then each thread will generate only one memory request, and then this one memory request will occupy the hardware resources of the error data cache, such as the PAG or MSHRs. Okay, good. It's the somewhat good case. So it's the optimal case. Some applications may access data irregularly. So this kind of memory transactions, so which means that every thread access the nearby data element in the memory space, then this kind of memory request is called the regular accesses. But some application, so actually some application can access the different can access our data element regularly. So which means that, so in this example, there are multiple threads here, and then this is the cache lines. And then, as you can see, this is one graph. And from the single graph, is a multiple thread that we can stop different memory address. So the different cache line spaces. Okay, so actually this example, in this example, the memory requests are regularly assigned, then these 8 threads will generate only one memory transaction. But this example shows that number of threads are the same. Number of threads is the same, the eight thread, but 8 thread generate the full cache line request. So sometimes some applications generate the memory transactions like this. And then actually it's so CPU domain, so it's a CPU domain. This type of memory access patterns are very common. Okay. So because and then so if multiple threads are executed, and then actually these multiple threads are independent kind of program code. So actually these multiple threads may exhibit the irregular accesses among multiple threads, and it's very obvious. But in a GPU, the multiple threads are generated from the single kernel, and then actually the index I for the data array is mapped to the single thread of the GPU. So actually we expect that the memory transactions generated from the multiple thread will work as the regular access patterns. For some application, it's not true. So there are many kinds of applications. So actually this expectation can be broken. So this kind of applications generate many transactions from a single one. So in this case, this one, even though one work is executed, and then this one work will generate the multiple memory transactions, and the multiple memory transactions will occupy hardware resources of the cache. And then all hardware resources of the cache are occupied, then this cache cannot service the upcoming memory transactions anymore. So which means that the load instructions are also stored in the pipeline. So this is another some critical performance issues in a GPU. So which means that if the application exhibits the irregular memory access pattern, and then this type of applications exhibit the low performance, the GPU memory hierarchy. Because if the memory transactions are well correlated, it's merged well, then the performance of this application will be high, actually in the GPU memory hierarchy. But if an application exhibits the very irregular access patterns, then performance will be very low. So this is also another critical performance issues in the GPU architecture. So if a GPU handles the very regularly assigned data, such as the graphics or multimedia, or even linear algebra application, then this type of applications exhibit the regular access patterns, right? So these graphics applications, so pixel data are regularly assigned, located in the memory space. Okay, and then each thread will access each pixel data. Okay, so which means that the pixel data, the graphics application, the one normal graphics applications exhibit the very regular memory access pattern. Which means that in this case, the memory transactions are well correlated. So GPU's memory hierarchy is efficiently utilized. But some applications like the graph. So graph application is very different from the regularly assigned, regularly allocated application like graphics application or some multimedia application, because graph structures are also originally handled the irregularly connected data elements. Okay. So also the graph data are very sparse, so we frequently use the compressed graph structures, so like the CSR format, using the CSR format. Okay, so because the data in the graphs are irregularly connected, then not to analyze the these graph structures, these graph applications generate the many irregular accesses. So this kind of application is not good for the GPU architecture. Okay, so but graph applications are very critical for analyzing the stuff. Talking or some scientific analysis. Then also graph data size is very large, so if we use the graph GPU for this graph application, the performance can be improved, but the memory hierarchy of the GPU is not efficiently utilized because of its characteristics, regular access. Okay. This is also very critical for the performance of the GPU. So this is the example. So the wireless access and this is just included in the 128 byte size, but on-wireless access may cover the large amount of cache line space. Okay, so this is the example of the GPU kernel that shows the criticality of memory quality. This is just a simple data copy kernel. So, but as you can see, the index of the data is defined by block index and thread index like this. So it's defined the thread index x is added to this to calculate the XID. So block dimension is this is the constant, and then also this block index is determined by CTI ID, and then inside of the CTI, thread indexes are also determined. So what you can see, this is the X, so which means that the thread indexes are assigned like the 0, 1, 2, blah blah blah, 31, and then these threads will be grouped into a warp. So just remember that the warp is the hardware unit or software unit. So programmers does not know about the warp. Okay, but warp, the warp is the hardware unit of the GPU. So actually the performance of the GPU is highly influenced by the organization of the warp. Okay, but the software engineer does not know about the warp. Okay, but as you can see, we can find some offset here. So this graph shows the effective bandwidth of the GPU, and then also this is the offset. So if the offset is 0, and then also this GPU is the B100, this is somewhat modern GPU. So actually the problem is that we don't know the exact architecture of the GPU, right? Because GPU is the commodity processor. But if we see that this offset, if we change the offset, then we can measure the effective bandwidth of the GPU. So what is the observed? If the offset is 0, then the bandwidth is high, but the offset is 1 and until 7, right? Until 7, right? Until 7, then the bandwidth is reduced. Why? So it is because I said these threads are grouped into a warp, and then if the offset is 0, so as you can see, it is if the offset is the multiple of A, then the effective bandwidth is high, right? So which means that based on the offset, if the offset is 0, then this thread will generate only one transaction, right? Because offset is 0, then thread 0 will access this size of data, and thread 1 will access here, and then all thread in a warp will access one cache line space. Okay, so this quite very understood. So a warp will generate only one memory transaction. But if the offset is 1, then effective memory bandwidth is reduced. Why? It's like this. So it's obvious, right? When the offset is 0, then it's well coalesced. But if the offset is 1, then the thread in the warp will request this data is like this. So, but as you can see, this is not aligned in the cache line size because of the offset. So in this case, a warp will generate one request for this data request, then the second request for the remaining data. Okay, so if the offset is the multiple of A, then it will generate one memory transaction. But if this request is not aligned, then it will generate two memory requests. So based on so actually this is also well coalesced except the offset part. So if the offset is 2, then it will also generate two memory requests. Right? So because it's a well aligned memory request. Okay. So then if the offset is 8, and it will also generate one memory. So effective bandwidth is increased. Also, I showed this graph the previous class. Actually in this example we just changed the stride. Okay, so stride means that the thread, if the stride is 1, then the thread will access the next data element. But if the stride is 2, then the neighbor thread will access the gap will be increased. So like this. Then if the stride 3, then the distance will be longer. Okay? So as you can see, what's the problem? If the stride is 1, then the transactions from the thread in the warp will be well coalesced. So it will generate only one memory transaction. So you can find that the effective memory bandwidth is the 800 megabytes per second. It's a well coalesced. But the stride becomes the 2, then it will generate I expect a single warp will generate 2 memory transactions. Okay, and then 3, then it will generate multiple memory transactions. So If a single warp generates multiple memory transactions, then the effective bandwidth will be reduced. Okay, this is the impact of the memory policy. But you may be curious about. So it means, so actually, if the stride is 1, the effective memory bandwidth is the 800 gigabytes per second. Actually, the GPU is the same, the B100. So it's the same to the 800 gigabytes per second if the offset is 0. But if the offset is 1, then I said that a single hop will generate the 2 memory transactions. But the effective bandwidth is the 700 gigabytes per second. It is reduced. But if the stride becomes the 2, then the effective bandwidth is reduced to the under 300 gigabytes per second. And then I believe if the stride becomes 2, then it will generate 2 memories per watt. What is different? So in this case, so if the offset becomes 1, then I also expect that a single warp will generate 2 memory transactions. So it's the same. If the stride becomes 2, then a single warp will generate the 2 memory transactions. What is different? Why can we observe differences between this case and this case? Why? The same. I said for the previous slide, it's 2 transactions per warp. Also, in the slide, I said that if the stride is 2, then it will generate 2 memory transactions per warp. But effective memory bandwidth is so different. 300 megabytes per second. Then the previous slide, we can observe 700 megabytes per second. What is different? Is it because of cache? So in the previous slide, a warp will generate the 2 memory transactions. But so I also in the previous class I also mentioned that the GPU core, the GPU string multiprocessor, supports the fine-grained multiplier. So which means that firstly the warp 0 is executed, and after that warp 1 is executed, and warp 2 is executed. So even though a warp is generate the 2 memory transactions, but data by the transactions will be cached, error data cache. So warp 0 will request this amount of data, and then warp 2 will request this amount of data. But if we see the alignment in the cache line, even though this data is requested by warp 0, this amount of this cache block is already requested by level 1 data cache, and amount of this data is found in the level 1 cache. So after that, warp 1 requests the load instruction. Then this warp 1 will also generate 2 memory transactions, like 1 and 2, this, but this memory transaction 1 will exceed the cache hit because already this cache line is replaced by regular cache. So this one can find this amount of data inside of the background cache. So actually, this is the cache miss, and then one request is generated from the background cache. But if we just change the stride, then if the stride is 2, then what 0 will request this amount of data, and then what 1 will request this amount of data. Okay, so the number of transactions are the same, but we cannot observe any cache hit between the request from WAP 0 and the request from WAP 1. Okay, so this is also this is the cache miss. This is the cache miss. Okay, because of this difference, then if we just change the stride, then the values is dramatically reduced. So that's why the GPU analysis is much more difficult than the CPU because when we just analyze the performance of the CPU, then we can focus on the performance of 1 and 2 threads. So if we just focus on the performance of the single core, like the independent core, then this single core can execute the 1 and 2 thread, or usually 1 thread. But listen, if the core supports the hyper-threading, Intel hyper-threading, then this single core will also run two threads, up to 2 threads, right? So you can easily analyze that. It's not easy. Actually, it's not easy, but we can maybe reasonably analyze the performance impact of the thread, the CPU core. But GPU, actually, the GPU SM, the single SM, runs the multiple threads, and then actually the multiple works. Okay, so this work is similar to the single CD instruction. So it's not different, but we can say we can just handle like is what is the one CD instruction. But GPU also runs the multiple works, and then these multiple works share the same memory hierarchy, the SM. And we attach or share the memory, blah, blah, blah. So it's not easy. It's more difficult to analyze the performance impact of these multiple threads or multiple works inside of the GPU. Right? Okay. So Aaron data class has the MSHR. Actually, we require the MSHR for supporting non-blocking cache. Okay. So we can MSHR keep the outstanding memory request, which means that if the miss occurs in a cache, and then this miss needs to be serviced from the low level cache, but it will take time. So while this event is handled by the cache, then without MSHR, then the upcoming request cannot be serviced from this cache. GPU cache also has the MSHR. So it's the same to the CPU. CPU has also, so the modern CPUs also use the MSHR because the blocking cache is very inefficient. In order to support the non-blocking cache, CPU has also the MSHR. But MSHR has also the limited hardware resources, which means that number of entries are also limited, which means number of entries besides the number of outstanding requests which can be handled by MSHR. Okay. Actually, the modern APU has the different cache structure for the second cache. The old generation is the cache structure is it's not like a cache. It's a similar to the normal conventional cache. But just remember the MSHR is also very precious the cache resources. And then if MSHR is full, then GPU also receive the trying to request the also if the memory access patterns are very irregular, which means that many presentations are given to the cache, then the MSHRs are also fully occupied, and in that case, the GPU cache cannot receive the services request, then the load instruction, load pipeline also blocked. So, and then for modern GPU increase the size of the MSHR. Okay. So actually, the NVIDIA tried to change the architecture of the GPU generation by generation. Okay, GPU also applies the different write policy. It's also some example. Okay, so if for the local memory space, and then in the Aaron data cache, if the write hit, then GPU is the write back. So which means that I believe you are familiar with the write back policy, which means this is the cache line, and then the cache line is updated by store instruction, and then this update is not immediately reflected to the low level cache. This is the write back policy. So for the local memory space, then GPU, for the write hit case, GPU supports the write back. But if the data is in the global memory, GPU will support the write edit policy. Why? It's related to the characteristics of GPU applications. So you know the GPU application, the size of the GPU kernel is actually very small compared to the CPU thread, because the CPU when the CPU thread is executed, then if this thread handles the large data, then the instructions are repeatedly executed for this large data, which means that the data, the update of this data should be reflected to the main memory by the CPU. But the GPU supports the parallel processing, so which means that the iterative loop of the CPU thread is converted into the multiple thread, not GPU. So for example, so this is the for loop in the CPU. So these are sequentially executed in the CPU. But in the GPU, these executions are changed to the multiple thread, which means that the size, the instruction size is smaller for each kernel. So which means that usually the final data is just stored in the main memory, and then the stored data is the just final data. So which means that this data will not be used again by the same kernel. You understand? So when the store instruction is executed, then it's just the final result, which means that so this result will not be reused by the instruction in the same kernel. Okay? That's why GPU for the right case, GPU does two. Error for the error data cache, GPU support the right edit. Which means oh, the right key. Store instruction is executed or the right key. And this cache line is updated, then this is evicted from the cache. And then for the right miss, so you can find the right miss case. So in the CPU, when the right miss occurs, then that cache line just becomes the one cache block. Okay, then the cache block is fetched. This cache block is fetched from the low level cache, and then cache block is updated. So this is how the CPU cache works. But as I mentioned, when the store instruction is executed, then this data will not be used in the GPU kernel with a high probability, not always. So that's why I explained that. So this policy is based on the characteristics of the GPU kernel. So for the write means then write no allocate. So which means that the write transactions just given to the low level cache. Okay. The same to the local memory and then global memory. But you don't know the exact policy of the NVIDIA GPU. So actually this policy is the policy from the GPU. Also, the data cache is not coherent. So GPU does not support the coherent protocol. Which, and you know, the GPU is the multiple streaming multiprocessor. So which means that when the store instruction is executed, then is the store instruction may update the same data in the multiple SM. But it could, for some papers discussed about the coherency in the GPU's multiple SMs, but so in the GPU hardware, the coherency is not considered because also GPU also support the simple memory connections. Okay, it's not coherent. And then the interconnection network. So you can see, you can find the interconnection network. So this interconnection network are connected to the multiple SMs and the multiple L2 partition. So actually this is the architecture, so structure of the interconnection network revealed by GPU. So as I mentioned, actually you don't know you get structure of the interconnection network, the commodity GPU. But so this is the cluster, and then the requests from the clusters are also including the injection buffer, and then the injection buffer collects the multiple requests from the multiple SMs, and then these requests are given to the interconnection network. Also, the CT core cluster received the responses from the interconnection network from the response bytecode, and then this response bytecode distribute the multiple multiple responses to the target SM. Okay, but we don't know the exact structure of the interconnection network. Also, we don't know the exact topology of the interconnection network in GPU. So this is the crossfire type, and then this is the mesh type. But for the modern Intel CPUs use this mesh network. It's a main type. The Intel CPU the old generation. Old generation use the ring type, but we don't know the exact structure of the interconnection network, the GPU. So actually, if you see the GPU the same, then we can also compute the topology of the interconnection network. So, but we usually use this cross-port type interconnection network. And so, now let's take a break for 10 minutes. Then I will cover the memory partitions of the GPU. Okay? Let's take a break for 10 minutes. I will begin at 11:52. Okay, let's resume the class. So, in GPU memory hierarchy, I explained about the error data cache, and interconnection network. So I will cover the memory partitions. So also, I use this figure frequently. So as you can see, we covered this interconnection network. Okay. So and then, as you can see, you can find the multiple memory partitions right here, and you can see the shared item cache. So in the inside of this memory partition, so these are called the memory partition. Then inside of this partition, we can find the level 2 cache and then memory controller and the external memory. So it's a GPU's device memory. Okay. So it is so actually this is the somewhat old old generation information, but so it is because the NVIDIA GPU changes their GPU architectures generation by generation. But we can also get some information from the papers about simulators. Yes. Then so also the NVIDIA can also change the number of memory partitions of the by GPU generations. So for example, GT200 has the 8 memory partition, and the Fermi has the 6 memory partition. What is related to actually animation? So each memory partition has its own memory controller, and which means that each own memory channels to the GPU device memory. Then how can we increase the bandwidth? So we can increase the bandwidth by increasing the memory clock frequency first. This is the right way to increase the memory bandwidth. So you can observe that memory clock frequency of the GDDR6, the model GDDR is very high. Also, we can increase the memory bandwidth by increasing the bus width to the memory chip. And then, GPU, we can increase the memory bandwidth by increasing the number of memory channels. Okay. So this is the architecture of the memory partition. So actually, this is based on the GPU CM. So each memory partition has each input port and then output port. And then, so this is the L2 cache. You can find the L2 cache here. So because the transactions are collected to this memory partition, these transactions to this target memory partitions are included in this interconnection to the L2 queue. So this is the base of also GPU model. And then if the data is not found in the L2 cache, then transactions are given to the DRAM memory controller. So actually, DPG machine implement the latencies between L2 cache to the DRAM using the DRAM latency queue. Okay, so it's not actually it's not easy to implement the real the latencies in the simulator because it's just the simulator, not hardware. So actually, the simulator has the GPU sync implement the latency between L2 to the DRAM using this DRAM latency queue. Okay, so if the given the transactions are given to the DRAM memory controller, then this controller access the option memory. But DPG also implemented just the timing model to the this object DRAM of the GPU. And then also the GPU has the ROP, the rest operation pipeline, but this ROP is not implemented in the simulator, just to the ROP implement the latency. Okay? So as I mentioned, the GPUs is the dedicated core processor for graphics applications, right? Actually, so the original purpose of the GPU is accelerating graphics applications. So, but we don't know. So we don't know the exact structure of these graphics pipelines, the GPU, because this is the out of our interest, right? Because we just focus on the structure architecture of the general architecture for general purpose GPU. So that's why ROP is not implemented in the GPU sim, but actually, but ROP latency is just implemented. So it's a very simple memory partition model, and then L2 cache write policy. So GPU NVIDIA also changes their cache policy by generation. Okay, so actually the L2 cache only caches the texture data for the G200. It's very old GPU, and then for the current architecture, the old memory spaces are cached in the L2 cache. So actually, so currently the L2 cache just caches the old data space, the memory transaction to the old data space, and then recently the modern GPU architecture like the RTX 4090 has very large cache, 2 megabytes. It is reported that RTX 4090 has very large cache. Okay, but so I believe it is because if we increase the cache size, then we can increase the also the performance of popular applications such as the neural networks, the AI application. And then if we see the right policy, then this right policy of the L2 cache is similar to the right policy of the normal cache. Okay? So for the right hit, the L2 cache has used the right back policy for the right hit. Then for the right in this case, the L2 cache applies the right allocate policy, which is same to the CPU's right policy, right cache policy. And DRAM. So actually, so DRAM is some very complicated system because DRAM is just it's a hardware. So DRAM has some topology such as the low column, also bank, rank. So and then based on these different topology, like the different rank, low column, and then bank location, the access time is changing. Okay? So, but I will not cover the detailed operation of the DRAM in this class because this is the GPU course. But when we handle we already know that the bandwidth, the DRAM bandwidth is very critical for the performance of the GPU. Okay, that's what it is obvious because the GPU loads the multiple threads concurrently. The bandwidth is very critical. Then how can we increase the bandwidth? So we can just estimate the peak bandwidth of the EDR, like the DRAM, using DRAM frequency multiplied by the DRAM rate, like the QDR or DDR, and then multiplied by DRAM bit width. That is the peak bandwidth of the DRAM. But as you know, this is the peak, the theoretical bandwidth. And then usually we cannot reach this peak bandwidth of the DRAM. Is it because DRAM is also very complex system? So it means that actually DRAM has the very also some hierarchies such as the bank, rank, row, and column, and then also the DRAM requires refresh. Okay, while the DRAM cells are being refreshed, then we cannot use this refreshed cell during the refresh period. So peak performance is not just the peak performance; it's a theoretical performance, it's ideal performance. So we cannot reach this peak performance because the different row accessibility, column accessibility, and also the bank company. So also the DRAM has the low buffer. Actually, this low buffer is the sense amplifier. So when the address is given to a DRAM, this address is split into the column address and row address. Also, this address is also allocated to multiple banks. Okay, so address is split into the bank address, row address, and column address. And then, as you can see, this is the row buffer. And then when the address is given to a DRAM, using the row address, the entire row is read from the memory array of the DRAM. And then this entire row data is buffered in the row buffer. Actually, it's a sense amplifier, but it works like a buffer, so that's why we call this is the row buffer. And then this row is very wide. And then we read using the data using the column address. So there are multiple columns in the entire row, and then we can go to this column address, then we can read the data from the DRAM. Also, DRAM has the multiple banks, then also, which means that we can also explore the memory level parallelism of the DRAM. So, but if we cannot exploit this memory level parallelism, then at the low complete case, the DRAM performance is degraded. Okay? So, for example, if the row is accessed, and after that, the default row is accessed. So, in this case, the row data buffered in the row buffer should be updated to the original space, because when the row is read from read and then buffered in the row buffer, the data is damaged. And then when the row buffer is the data in the row buffer is changed, the original data is returned back to the DRAM memory space. Okay? So actually, DRAM does the very complex operation. Okay, so just remember that if the DRAM is not properly accessed, then we can reach the peak performance of the DRAM. Okay. So GPU also explores the DRAM memory level parallelism using the multiple banks and then multiple chips. Okay. So the GTX4A, the two chips, the two DRAM chips are connected to the single DRAM controller. Also, you can find multiple banks inside of the DRAM. But this number of banks are determined by DRAM specification. Samsung and Hynix manufacture the DRAM chip, then actually the number of banks, and then the timing of the banks, and then the ranks, and the column and row are determined by the hardware specification of the DRAM. Then DRAM controller access the data in the DRAM using this timing information, considering the timing info, the required timing information, the DRAM chip. Okay, so I covered until the DRAM of the GPU memory hierarchy. Any question? Okay, so let's move on to different next topic of the GPU. So until now, I covered the hardware architecture of the GPU. So I also covered the software execution model of the GPU architecture. And then now, I will briefly cover the simple CUDA programming model for popular computation kernel. So popular computation kernel is the matrix multiplication. So when we just mention the performance of the kernel, the computation kernel, that we frequently use the matrix multiplication. So it is because the matrix multiplications are widely used by parallel programs. So if you learn about some parallel programming, then you will also learn about the parallel programming of the matrix multiplication, which means that we can implement the matrix multiplication using pthread or OpenMP in a CPU domain. So that's why it is because the the matrix multiplications that are widely used by common computation application. So it's the same to the GPU. So this is the very popular kernel of the GPU programming. So I will use this matrix multiplication kernel as an example of the program. So this is the programmer's view of the GPU's memory space. So actually, the programmer knows that if the data is read from the global memory, it will take very long time. But programmer does not know about the detailed space, detailed architecture, detailed memory hierarchy of the GPU or GPU. Right? In a CPU domain, the CPU, there are two kinds of instruction like add x1, R1. X1 is the register of the RISC-V. R1, R2, R3, or load R1, R2, and immediate. So this is this instruction, the add and the load. The add instruction just handles the data in the register file, but then also this is the assembly code. So which means that this is also a software, So we already know that when the data is read, fetched from the register file, then this will take this instruction will be executed very quickly. But if you see this instruction, we can find only register amount, right? So we can find, oh, it will take it will be executed very quickly. But load instruction access the memory. So, and then if the data is found in the main memory, then it will take very long time, right? So the programmer's view, programmers doesn't just consider the data in register file or data in global memory. That's it. It is because the CPU, the cache hierarchy is automatically managed by hardware. The programmers cannot manage data inside of the cache because it is automatically managed. So this is the two data space of the CPU domain, the register file and global memory. But the GPU has many memory spaces as we learn. So actually, to the programmer's view, the GPU has more memory spaces. The first one is the register, because the GPU also has the RISC type instruction R1, R2, R3, which means that to the programmer, if a programmer sees this assembly code, then the programmer can know that this instruction just access the register file, so it will be very fast. So we assume that in order to access the register file, then it will take only 1 second. And the GPU has the shared memory, as I mentioned, and then shared memory is actually scratch pad memory. So this scratch pad memory can be managed by programmer, like load shared. So shared memory is dedicated memory inside of a streaming multiprocessor, and then it will be very fast, right? So to the programmer's view, a register file is the fastest memory. It will take only 1 cycle. And then shared memory is also fast memory. So programmers think that it will take around 5 cycles here. And GPU also supports the global memory. So when the global memory is accessed, and GPU uses the load.global. Okay. So in this case, actually I mentioned that the GPU also has the cache hierarchy. So there are multi-level caches, but the cache is not seen to the programmers. The programmer think that the data, if the load.global is executed, the data is read from the global memory, GPU's device memory. So it will take hundreds of cycles. So this is the programmer's view. Okay, like 100 or 5. It can take the 500 cycles or even 1,000 cycles. We don't know, but programmers think that when the global memory is accessed, it will take very long time. And then another memory space is the constant memory. Like we can. And the constant memory is accessed with the load.const instruction, and this constant. So I mentioned that the parameters, the shared parameters are stored in the constant memory, and then this constant memory is read-only memory, and then also GPU has the constant cache, and these parameters are firstly loaded from the global memory, GPU's device memory, then the parameters will be fetched the constant cache. So, because these parameters are widely used among multiple threads, and then firstly it is loaded, and it is when the data is read from the constant hash, that it will take maybe two cycles. Okay, so it can be fetched very quickly. Okay, that is the Florence view of the GPU's memory space. Right, so because the GPU has the more memory space compared to the CPU domain, actually the program needs to handle these different memory spaces in the CUDA code. So let's see the matrix multiplication column. How can we handle the matrix multiplication using CUDA code? So then, in the CPU code, how can we write the matrix multiplication column? We just focus on the result of the target matrix, right? So, which means that this is the example of the matrix multiplication, like the P equal M multiplied by N. So these are matrices, and then size of width by width. Okay. Then when we write a matrix multiplication code, then we just focus on the element of individual element of result matrices P. Then by using the iterative loop, the CPU calculate the result for each element from top to bottom serially. Okay. Then how can we write the matrix multiplication code using CUDA? CUDA supports the parallel programming. So we can also just focus on the result value of the each element in matrix P. And how can we assign thread? We can assign thread for each element in matrix P. So, which means that a single thread is allocated to a single element in matrix, result matrix P. So we can write a CUDA code like this. So in the CPU code, we can calculate the result of each element of a result matrix P using the iterative loop, right? But in the GPU, these iterative loops are changed into the multiple thread. So each thread generates the result of each element in result matrix P. It's how the CUDA program is built using the multiple thread. And then also, how can we access the data in the matrix M or matrix N? Because in order to calculate the result of this element, then we need to require, so this is the N by N matrix multiplication, we need to require the data, the raw data of the matrix M. Also, we need to read the column data, entire column data of matrix N, right? So, in order to read data from the matrix M and N, so this is the 2D matrix, like X by Y, but when these matrix elements are assigned the memory, these elements are allocated the memory with the 1D format. That's true, right? So even though we can write, we can generate the multi-dimension arrays, but this multi-dimensional arrays are allocated to the memory like the one D array, right? It's obvious, right? Because just the memory is pointed by address on. Okay. So actually we frequently use the row major way of arrangement. The first row is assigned to the memory, like from here, and then the second row is assigned, then the third and fourth row is assigned. And how can we calculate the index of this element, the target element of the matrix? We can calculate the row index of the target matrix element like the row, the target row. So this is the target row multiplied by width of the matrix plus column. It's obvious, right? So this is the C code, the CPU's C code for the matrix multiplication. So I mentioned that the CPU just also focused on the target element, and then actually this result matrix P includes the multiple element, and so in order to calculate the multiple element in matrix P, then the CPU use the iterative loop. Okay? Then how can we read this column and this row and then column? So CPU by here. Okay, this is the iterative loop for the target element P, right? And here, and here. So in the target element, the index of the target element is the I, J, and then CPU use the iteration loop for the I and iteration loop for the J. So then, in order to calculate the result with the index K, K and K from this direction and then K for this direction, then the CPU scans the elements in the row of matrix P and then elements of this column of matrix N. So how can you calculate the index of this target element? I multiplied by this plus K, because so this is the I, and then by scanning each element of this row, so we can scan these multiple elements using the index K. And then this is different. It is the column, so K is multiplied by K multiplied by this. And then sum is calculated. This sum is stored to the target element of the result matrix P. Then, how can you write the CUDA code? So I said that for the CPU, it's iterative loop, and this iterative loop is used for generating repeated execution for the target element of the matrix P. And then these iteration loops need to be translated into the thread. But how? So when you learn about the GPU's execution model, the kernel first generate the thread blocks using the thread block in a grid dimension, and then each thread block generate the multiple thread. Okay. So actually, GPU kernel use the 3D dimensions for the grid dimension or thread dimension, and then so this result multiplex, the result matrix P can be firstly split into multiple blocks because we need to generate the multiple thread blocks was multiple CTAs, and then in each CTA was in each thread block is thread block includes the multiple thread. Okay, then how can we allocate the multiple threads, the thread blocks, and then corners? So we can split the large matrix into the multiple sub matrices. Okay, and then we can also define the block indexes like the 0, 0 and 0, 1, 1, 0, 1, 1, 1, and 1, 0. Okay, so this example shows that. So this is the 4 by 4 matrix, and then 4 by 4 matrix is split into 4 thread blocks or 4 CTAs. Then the dimension of a CTA is the 2,2. So there are 4 CTAs. And then in each CTA, we can find 4 threads. So actually the dimension of a thread is the 2,2 in each CTA. Okay. Also, if the matrix size is increased, then we can split the matrix P into the multiple more thread blocks and then thread. Okay. So with the grid dimension and the block dimension, then we can configure the size of the thread block and then size of the dimension of the grid. So which means that the large matrix P can be split into the multiple CTAs, and in each CTA, the multiple threads are assigned. So if we see that this dim block, then we can find that this is the dimension of the block, which means that dim block just decides the number of threads inside of each thread block. Okay, so this is the tie width and then tie width. Okay, so which means that one CTA will include the tie width multiplied by tie width thread. Okay, so this dim block is assigned, and because the large matrix P is also split into the multiple thread, and then also the size of this thread block, a multiple thread CTA, and then the size of the CTA is the tie width multiplied by tie width. Then the dimension of this grid is defined like the width divided by tie width, and also the width divided by tie width. Okay, and then these dimensions are sent here, and then this is the matrix multiplication of the GPU. So this is the host side code. So in the CUDA is executed, then the dimension of the thread block and the dimension of the thread are also defined in the host side. Then using these dimensions, the multiple threads are generated for this kernel, and then that is kernel. When the kernel is launched, these multiple threads are initiated in the GPU hardware. Then, so the index of these elements need to be calculated using block dimension, then block index, and thread dimension and thread index. Okay, because these matrices are, this matrix is split into the multiple CTAs, and then multiple thread in a CTA. The index of the CTA is defined by block index, and then the index of the thread inside of the CTA is determined by thread index. So the index of these elements should be computed using this block index and the thread indexes. Okay. So let's see the example. So this is the matrix multiplication kernel inside of the matrix multiplication kernel for the CUDA, for GPU. So you can find that for the row and column of the target, then you can find that the row and column of the target is determined by block index, and then block dimension, and then thread index 1. Okay, so it's like this. So oops. You have to index this one. Okay. We first determine this index of the block, and then inside of this block, then we just use the thread index, and we can calculate the location of the thread in the thread index. We first figure out the location of the thread block using the block indexes, and then inside of the block, the location of the thread using the thread indexes. So the row is the block index 1 multiplied by block index of y and plus thread index 1. So this is the location of the block. Then inside of the block, the row is determined by thread index at y. And also column is the same. Column is determined by block index at x, multiplied by block dimension x, okay, and thread index at x. Okay. So in a GPU, you have to calculate the indexes. So many threads are generated from a kernel. So and actually each thread has its own indexes. Each thread has its own index. So and then these indexes are determined by block indexes and thread indexes. Okay, this is because the first list from the kernel, the CTAs thread blocks are generated, and then in each CTA, the multiple threads are generated. Okay, so if you see this CUDA code, you can find that this CUDA code has only one iteration loop. Okay, and then in this iterative loop, the k is just changed. It's like in the CPU code has the 3 iterative loops, but this loop is changed to the thread. So this loop is erased, is removed in the GPU kernel. So only this loop is executed. Okay. So this is the loop inside of the kernel. So first, as I mentioned, each element of the matrix P is converted into the thread in the GPU kernel. And then inside of the kernel, then we need to also read the row data from the matrix B, and then column data from the matrix N. And how can you calculate the index of the matrix M and N? You just send it to the CPU. Okay. So in order to calculate the indexes of the matrices M and N, we also use the row and column number of the target matrix. So it's the same. So in this example, the K is changing from 0 to V. Then using the row, then K, and then we can calculate the required element from the matrix N, and then also K and column, and we can also calculate the required element from matrix N. So this, because this is the read operation, so the read from the matrix or matrix elements stored in the global memory, then we can just calculate the index of the matrix M and N. Okay, this one. So what is changing? Only this one is changing. The indexes, block indexes, and then thread indexes are required for each thread in a GPU. And then block indexes and thread indexes are calculated using indexes and dimension of block dimension. Okay. Then this calculate that this one is a stored. So this is the some example of the matrix multiplication column. Okay. So what changes from the CPU column? The only change is that this part. Okay. This part is changing. So just remember that when the CPU code is ported to the GPU code, then the iterative loop part is changed to the multiple thread. And then not to execute the multiple thread, then we need to define the block indexes and then thread indexes. So which means that we can also define the size of block, also size of the dimension of CTA or dimension of thread inside of the CTA. Okay. So, but then how can so when we learned about the SM hardware configuration, the SM has its own number of threads, which means that the maximum number of threads or maximum number of CTH. Okay. So we can split the matrix, the target matrix using the multiple block sizes like 8 by 8 or 16 by 16 or 32 by 32 blocks. So when we use the 8 by 8 blocks, then which means that the single CTA includes the 64 thread. Okay, and then actually for the Fermi architecture like a GTX 480, each SM can have each SM can run 1536 threads concurrently. Okay, and then also, and then this each SM only supports the 8 CTAs. This is the maximum number of CTAs. So what is the problem? So in this case, the block size is a single block has the 64 threads. So 64 threads is the actually 2 words, and then each SM can up to 8 CTAs. So which means that if the CTAs are assigned to SM, then only 8 CTAs are assigned. Then the number of threads is the 8 multiplied by 64, which is the 512. So what's the problem? Each SM can run up to 1536 threads, but with this configuration, the CTA size or block size is the 8 by 8, and each CTA includes only 64 threads. So if this SM can run only 512 threads, even though the maximum number is the 1536. So, and then if the CTA size is the 16 by 16, then each CTA includes the 256 thread, and then for this case, then each SM can include only 6 blocks. But when the 6 blocks are included, then this SM can run 1536 threads concurrently, right? 6 multiplied by 256. So in this case, when the CTA size is too small, right, then the performance, the SM capacity is limited by number of CTAs in this case. But if CTA size is reasonable, then in this case, the number of threads inside our SM is limited by thread. Okay, so which means that 6 CTAs are assigned to the SM, then this SM can run maximum number of threads. Okay, which means that we can make use of the maximum TAP for this case. But for this former case, then on SM can run only 512 threads, which means that we do not take advantage of the TLP of the SM for this case. Only 512 threads are running. How about the 32 by 32? So in this case, a single CTA includes the 1024 thread. What's the problem? The CTA size is too large, and then if the 2 CTAs are assigned to an SM, then we will run 2048 threads, but this number is larger than the 1536 threads. So in this case, also the SM's number of concurrent thread is limited by thread number, but problem is that this SM, if this SM includes the 2 CTAs, then the number of threads exceeds the maximum capacity of the SM. So the SM can only run 1 CTA. And then 1 CTA includes the 1024 thread. And then which means that 1024 is less than 1536. So which means we cannot take advantage of the maximum TLP of the SM. So what I want to say is that based on the dimension of the CTA, then we may not take advantage of the maximum TLP of the GPU hardware, because GPU's SM has the maximum number of CTAs, or GPU maximum number of threads supported by GPU's each SM. So actually, when the CTA dimensions are considered, then we need to consider the maximum TLP or maximum capacity of a target GPU. Okay. So if we just consider only TAP, the thread level parallelism of the GPU, this configuration is the best configuration because it makes use of the maximum number of threads which can be supported by SM. Okay. If the compute size is different, then we cannot make use of the maximum TLP of the SM. Okay. So the performance can be also influenced by this CTA size. It's interesting, right? So I'll stop here. Any question? Okay, so thank you for your attention, and then in the next class. 감사합니다. GPU가 좀 우리 뭔가 하드웨어랑 소프트웨어랑 그럴 게 많아가지고 저도 좀 힘들고